Good morning to all of you. Let us do a summary of what we did in the previous class and then proceed further. So what did we set out to achieve? Let me make a list of that once again. So in the previous class we stated why study solid state devices, we sketched the current voltage characteristics of a p-n junction, bipolar junction transistor and a metal oxide semiconductor field effect transistor. Then we described the evolution of solid state devices, namely diodes and transistors. Then we stated the steps involved in analyzing a solid state device to obtain an equation for its current voltage characteristics. Then we started describing how mobile charges are generated and transported in semiconductors. So that is what we want to proceed with in this class, and further we will see how to distinguish between a BJT and a MOSFET. In fact, some differences between BJT and MOSFET were pointed out to you when sketching their characteristics already. Then we plan to explain the rectifying operation of a p-n junction and amplifying operation of a transistor, bipolar and MOS without using equations or energy band diagrams. So purely using reasoning, this is called qualitative explanation, right, which does not involve any sophisticated equations. Then it depends on whether we have sufficient time in this session today. Otherwise, in the next session we will explain the features and utility of the energy band diagram of a semiconductor. Then we will write and explain the equations based on drift diffusion carrier transport that are employed to model a solid state device. We will state some standard approximations employed to simplify the solution of the above equations. And finally, we will state how to check and remember device model equation and what precautions should be taken while making calculations with it. So I am doing a summary of what we did in the previous class. We looked at some small signal diodes and transistors. So diodes are 2-terminal devices, transistors are 3, or as we have seen in the case of MOSFET, could be a 4-terminal device. Then we saw that power devices are much bigger than small signal devices, and they have a provision for attaching them to the heat sink, which dissipates the power generated in these devices, right, so that the temperature of this device doesn't go up. Then we saw microwave devices. The packages of these devices are different from those of other devices. They ensure that parasitic capacitances and inductances are very, very small. Then we considered the symbols of diodes and transistors. We explained that we study solid state devices because solid state devices are all around us. They enhance performance, reliability and cost effectiveness of energy systems and information systems. So energy system is the one which generates, distributes and regulates as large an energy as possible. Example of this is, for example, a switch mode power supply, okay, which is used to power your computer when the power supply is not there. The information system, on the other hand, stores, processes and communicates information expending as small an energy as possible. Your cell phone, the computer, all these are information systems. We gave some examples of how solid state devices has revolutionized our life, right. So here is an example of mechanical and electronic calculator. Mechanical calculator used many tens of years ago and electronic calculator used today. Similarly, we saw some sensors, how very small size devices like this can sense very many things, from temperature to acceleration, pressure and so on. Then we sketched the current voltage characteristics, right, of different devices. We started with the p-n junction. We sketched the DC current voltage characteristics, and we mentioned that it is very important to remember what are the axes, x and y axis, right, and what are the values that are used here in plotting the current voltage curve. For example, commonly the diode current voltage curve is plotted with positive y axis in milliamperes, whereas negative y axis in nanoamperes, because reverse current is of the order of nanoamperes and forward current is of the order of milliamperes in small signal devices. In power devices things are different, but even in those devices, that is power diodes, the positive y axis will correspond to high current levels as compared to negative y axis, right, which shows the reverse characteristics. So always there will be orders of magnitude difference between currents plotted on the positive y-axis and negative y-axis. So this we must remember, because only on such an axis you see a change in the slope near the origin of the current voltage curve. So we also showed how the same curve looks like if you use the same values of current in both positive y and negative y-axis. So here is an example of current voltage curve with milliampere current range, and here is an example of current voltage curve with nanoampere range in positive and negative axis. Similarly, we sketched the characteristics of bipolar junction transistor. So we said that there are three possible sets of curves: common emitter, common base, common collector, because bipolar is a three-terminal device. And we commonly look at the common emitter characteristics. Now we have both output characteristics as well as input characteristics. Then we sketch the current voltage characteristics of a MOSFET. Here it is a four-terminal device. So you have three power supplies. In BJT there were two, right? One was a voltage supply. Let us look back. So one was a voltage supply between collector and emitter, and a current source between emitter and base. On the other hand, the the MOSFET is a fully voltage controlled device. So you see only voltages here, and there are three voltages because there are four terminals. So we sketch the output characteristics, which are drain current versus drain to source voltage, and gate to source voltage is the controlling parameter, and gate to source voltage in the MOSFET is analogous to the base current in the BJT. So we said that between MOSFET and BJT, one of the differences is that MOSFET is entirely a voltage controlled device, whereas the BJT can be regarded either as a voltage or as a current control device. Now we don't have any input characteristics for MOSFET, current voltage input characteristics, because the controlling terminal, namely the gate, does not allow any current. So this is one more difference between the MOSFET and the BJT. BJT has input current voltage characteristics, but MOSFET does not have. Then we looked at the evolution of solid state devices. So we showed how from 1870s different devices were proposed, right? They were either discovered or they were invented. Then we listed out the steps in which any solid state device can be analyzed. So we said essentially there are three steps: partition the device into space charge and neutral regions, step 1. Step 2, analyze each region separately to obtain the distributions of electrons, holes and potential, and then combine the information regarding electron concentration, hole concentration and potential obtained in different regions, ensuring continuity of these parameters across boundaries, separating the regions to obtain the complete picture regarding the terminal current as a function of the voltage applied between the device terminals. So these are the three steps in which we analyze any device. In fact, the word analysis itself means separation of the whole into parts, understanding the parts in isolation, and combining the understanding of the parts to understand the whole. And now we started off with description of how carriers are generated and transported in a semiconductor, because to analyze a solid state device, after partitioning the device into space charge and neutral regions, we need to obtain the electron and hole concentrations and potential, right? That is our goal. So if you want to get distributions of electrons, holes and potential, first we should know how electrons and holes are created in a semiconductor, right? And when you apply external voltage, what is the potential distribution inside the device? So that is what we are trying to do in the beginning. We looked at the atomic arrangement in a silicon crystal, and we said that every atom is bonded to 4 neighbors. Therefore, the three-dimensional crystal can be shown in 2 dimensions, okay, in this manner. Then we looked at intrinsic silicon, and we said at 0 Kelvin there are no electrons or holes or no mobile carriers. So at 0 Kelvin silicon does not conduct any electricity. Then we said that when you raise the temperature, the atoms start vibrating, right, as shown here, and these vibrations are random, and some of the vibrations are so violent that the bonds near that atom break, giving rise to an electron hole pair. Now this is what we showed in the next slide. So you see here generation of electron hole pairs, Now at any instant you will have certain number of electron hole pairs, and as a function of time the electron and hole concentration will be constant even though carriers are continuously generated, because the generation is counterbalanced by a recombination process in which at one point an electron and hole pair is generated because the silicon bond breaks. At the same instant somewhere else an electron and hole recombines, okay, and both are lost. It's somewhat like people are born in some place and some other place they are dying, and because the birth rate is equal to death rate, population is remaining constant. Now not only that birth rate is equal to death rate, the human beings which are born, they remain alive for some time, so that is called the lifetime. Similarly, even in the semiconductor, electrons and holes, after they are generated they remain for some time and they have a non-zero lifetime. That is why you have a population. In intrinsic semiconductor, electron and hole concentrations are equal. The hole is somewhat like a bubble in a liquid. So just as when you fill up a tube with liquid and there is a small air bubble, when you tilt the tube it is a liquid which moves around, but the movement of the liquid appears to us in the form of movement of the bubble, and the direction of movement of the bubble is opposite to the direction of the movement of the liquid. Therefore in the context of semiconductors, this vacancy or broken silicon bond which moves around because of the movement of other bonded electrons into these vacancies is given a positive charge, because the direction of motion of this vacancy is opposite to the direction of motion of the electrons. Therefore the charges are opposite. Then we began a discussion of the extrinsic semiconductor, that is what happens if you introduce dopants. So first we start with phosphorus doping. Phosphorus is a group 5 impurity and silicon is group 4. So when you put a phosphorus atom in silicon, then the fifth electron is not participating in bonding and therefore it revolves around the phosphorus atom. So without the fifth electron, the phosphorus atom is positively charged, because with 5 electrons in the outermost orbit, phosphorus atom is neutral. So without the fifth electron it is positively charged, and so the picture is somewhat like this as shown here. Now at t equal to 0 k, all the electrons are the electrons corresponding to the phosphorus atom are all revolving around the phosphorus atom and they are bonded. However, the force of attraction between the electron and the positive charge is much lower than it would be in vacuum, because as we mentioned in the previous class, silicon dielectric constant is much more than the dielectric constant of vacuum. Dielectric constant of silicon is 12, whereas dielectric constant of vacuum is 1, right? So if you want to write the expression for permittivity, permittivity is given by the relative dielectric constant into epsilon naught, and these two are epsilon r's, right? This is epsilon r for silicon and this is epsilon r for vacuum. So because of this large dielectric constant, the force between charges is reduced. The force between charges is given by q1 q2 by 4 pi epsilon into r square, where r is the distance. So if you have two charges, right, suppose I have two charges, positive and negative, minus q1 and q2, and distance between them is r, then this is the formula for the force. So you can see that if epsilon r is more, the force is less. In fact, if you calculate the energy of this electron revolving around the phosphorus atom using the hydrogen model, Bohr's model of the hydrogen atom, then you will find that the energy is inversely proportional to square of epsilon r. Force is inversely proportional to epsilon r, but the energy is inversely proportional to epsilon r square, which means if I square 12 I will get 144. So energy of this fifth electron will be 1 by 144 times the energy you will get for an electron revolving around a positively charged nucleus in vacuum, and that is why the bond energy between this fifth electron and the phosphorus atom is very small compared to the silicon-silicon bond energy. So silicon-silicon bond energy is 1.1 electron volt, whereas the phosphorus 5th electron bond energy is 0.045 electron volts. So it is so much smaller than this. So now what is going to happen when I raise the temperature? So at 300 K, all the phosphorus atoms will give away their electrons, right? Because why? Because average energy of particles at room temperature is kT. So if you try to find out the average thermal energy of silicon lattice vibrations, right? So the energy will be kT. Now kT at room temperature is 0.026 electron volts. In other words, we can think of a silicon crystal at room temperature as consisting of vibrational energy particles. They are called phonons of energy 0.026 electron volts moving about everywhere. They collide with silicon atoms and they give rise to, they break the bonds. So this is the way you can visualize the effect of silicon atomic vibrations, right? So at room temperature it is very difficult to break silicon bonds. That is why you have a small concentration of electrons and holes, electron hole pairs. Ni, which is the concentration of electrons and holes at 300 K in intrinsic semiconductor. I stands for intrinsic. So this is about 1.5 into 10 power 10 per centimeter cube. So this is in pure silicon. That is, go back to this slide and you see here Ni equal to Pi. I am giving you the value of Ni. 1.5 10 power 10. Now you might say that 10 power 10 is a very large number. Now you should know that no number is really large or small by itself. Okay. For example, if somebody says that I have 14 children. Now 14 children, is it a large number of children? Somebody says in a family that I have 14 children, I have given birth to 14 children. Is 14 a large number? You will say yes, very large, because nowadays families have only 1 or 2 or at most 3 children. So you see, in this context the number 14 is very large, right? In some other context, however, number 14 would not be large at all. So similarly, the number 10 power 10 may appear absolutely large, but it is not large as compared to the number of silicon atoms. What is the number of silicon atoms? So number of silicon atoms in a crystal is 5 into 10 power 22 per centimeter cube. So many silicon atoms are there in a silicon crystal. We just saw the 3-dimensional picture of silicon atoms, right? So that arrangement gives you 5 into 10 power 22 atoms per centimeter cube. Now compare this 5 into 10 power 22 with this number 1.5 into 10 power 10. If I take the ratio, let us call this as capital N. If I take the ratio Ni by N, that will be 1.5 into 10 power 10 by 5 into 10 power 22. Now this is equal to, so I can take it as 15 into 10 power 9, and 10 power 9 by 10 power 22 will be 22 minus 9 is 13, and this is 3. So what does it mean? Ni by N is 3 by 10 power 13. This means for every 10 power 13 silicon atoms, only 3 silicon atoms the bonds will break to give rise to electron hole pairs in an intrinsic semiconductor or pure semiconductor. You can see that this number is really small. Out of 10 power 13 atoms, only 3 bonds are, for 3 silicon atoms the bonds are broken. Okay. So this is really small number. Now as compared to this, for a phosphorus doped silicon, what will happen is all the phosphorus atoms will get ionized, while only 3 out of 10 power 13 silicon atoms get ionized in pure semiconductor, pure silicon. All the phosphorus atoms which you have introduced in the silicon crystal will get ionized, because the energy, bond energy of phosphorus, fifth electron of the phosphorus to the nucleus of phosphorus is 0.045, whereas the bond energy of silicon to silicon is 1.1 electron volt. So you need more energy to break the silicon-silicon bond as compared to the phosphorus fifth atom, fifth electron silicon bond. So therefore that is what is shown here, that at 300 K all phosphorus atoms will give away their electrons as free electrons. Now in addition, you will also have silicon bonds breaking, right, as in a pure silicon crystal. However, as we will see, if phosphorus gives rise to electrons, free electrons, the number of electron hole pairs which are generated by breaking of silicon bonds will reduce as compared to the number of electron hole pairs generated in pure silicon. Now the generation has to be balanced by recombination, therefore you will also have electron hole pair recombination. So the same rate at which electron hole pairs are generated, they will recombine, and that is why you will now have a steady concentration of electrons and holes. Now in pure silicon, number of electrons was equal to number of holes, whereas in phosphorus doped silicon you have number of electrons is equal to number of phosphorus atoms, right, which give rise to electrons, plus the number of electron hole pairs, that is represented here as number of holes, because for in every electron hole pair generation you create an electron as well as a hole. So number of electrons in a p type in a phosphorus doped silicon is equal to the number of phosphorus atoms plus the number of holes. That is what is written here. Now in practice what is going to happen is, what is not clear here, Nd is much greater than holes. Now let me explain to you what does the symbol N0 mean. So N means the electron concentration, suffix N means N type semiconductor, because phosphorus is a donor impurity, and suffix 0 here, the suffix 0 means equilibrium, that is no other influence of energy other than temperature on silicon. It is an isolated silicon piece, you are not applying any voltage, you are not shining any light, okay. So it is isolated, the only energy is thermal energy. Such a sample is said to be in equilibrium. So the suffix 0 here means equilibrium. So the equilibrium concentration of electrons in N type semiconductor is equal to number of donors, that is the donor doping concentration. Suffix D represents donors because it is donating an electron, and Pn0 means number of holes or concentration of holes in N type semiconductor, and 0 means equilibrium. So now since Nd is much greater than Pn0, your equation becomes Nn0 is approximately equal to Nd. So in a phosphorus doped silicon crystal, the number of free electrons will almost be equal to the number of phosphorus atoms. Now let us do the same thing for boron. What happens for a boron doped silicon? So boron doped silicon, boron is a group 3, so phosphorus is group 5, boron is group 3. This means it has 3 electrons in outermost orbit, every boron atom, whereas silicon has 4 electrons, and therefore if you put a boron in silicon, there will be deficit of 1 electron as far as boron atom is concerned, and that is why one bond will be broken. That is what is shown here. So you can see here that the broken bond is being shown as a whole because it is like a vacancy. So you can regard a boron atom as a negatively charged nucleus, because when a boron atom gets an electron from silicon, it gets negatively charged, because without the electron, it has 3 electrons in outermost orbit, it is neutral. If it gets an additional electron, then it becomes negatively charged. So that is why here you can see that it is making bonds with 4 silicon atoms, but in the process it has got negatively charged, and that electron has been picked up from a nearby silicon atom, and therefore that bond has broken, and that is like a hole, but this hole is bonded to this negatively charged impurity, and it can be regarded as revolving around the boron nucleus, just like for the case of phosphorus. So phosphorus, the model was a positively charged nucleus. You can see that here. Phosphorus was positively charged nucleus, an electron revolving around it. The boron at t equal to 0 K is negatively charged nucleus with a positive charge or hole revolving around it. Now at 300 K, all the holes will become free. In the same way as all the electrons of phosphorus atom became free, the bonding energy between the hole and the boron atom is the same as bonding energy between the 5th electron and the phosphorus atom, right? It is the same model, and 0.045 electron volt, which is much less than the energy of the silicon bond. Therefore all boron atoms become ionized and they give rise to holes. So you have an additional process in which electron hole pairs are created because of breaking of silicon bonds, but this number will be small because the bond strength of silicon is more. So you see here a few electron hole pairs, and generation will be balanced by recombination. Therefore you have equal number of electron hole pairs being generated and recombining at any instant, giving rise to a steady concentration. Now the expression for holes in a p-type semiconductor is given here. So hole concentration in p-type semiconductor, therefore this suffix p and suffix 0 shows equilibrium. So hole concentration in a p-type semiconductor equilibrium is equal to the concentration of acceptor impurities, Na. Boron is called an acceptor impurity because it accepts an electron from a nearby silicon atom to become ionized, plus Np0, that is number of electrons in the p-type semiconductor, right? These are electron hole pairs created by thermal generation. Once again, Na is much more than Np0. So doping is much more than electron concentration or minority carrier concentration. So here electrons are minority carriers. In a p-type semiconductor, number of electrons is less than number of holes, therefore electrons are minority carriers. In an n-type semiconductor, number of holes is less than number of electrons, therefore holes are minority carriers. And since Na is much more than Np0, you get Pp0 is Na. So hole concentration in a p-type semiconductor will be equal to the doping concentration of boron. Now this is how we have understood how carriers are created in semiconductor, right? So we have said that there are two processes by which carriers can be created. One is called impurity ionization. If you are introducing impurity in the semiconductor in the form of phosphorus or boron, then those impurities get ionized at room temperature and they give away free carriers. And you also have thermal generation. So silicon bonds breaking and ionizing. So these are the two sources of carriers in semiconductor. Now let me put a letter against each of the processes. So here, for example, an electron hole pair is being generated, so I put the symbol G. So in this location of the crystal there is generation. Similarly, I have put G in all the locations where an electron hole pair is being generated. So you have two such locations here, and I have put the symbol R or the letter R wherever electron hole pairs are recombining, and I have put the letter I in locations where impurities are getting ionized. So this is impurity ionization. Okay. Now note that while electron hole pair generation, which is associated with silicon ionization, so when a silicon atom ionizes, you get both types of carriers, a hole and an electron. Whereas when an impurity ionizes, you get only one type of carrier, either an electron or a hole. You do not get both. If a phosphorus atom ionizes, you get a free electron, but you don't get a hole. If a boron atom ionizes, you get a hole, but you don't get an electron. But when a silicon atom ionizes, you get both electrons and holes, because breaking of a silicon bond creates a vacancy, and that vacancy is called a hole. So now I have removed the silicon bonds to make it a clear figure. You can see that at different locations how the carriers are being created by the process of generation So G here shows generation, R recombination, and I shows impurity ionization. This is what is happening in a crystal. At different points these phenomena are taking place. Now let us summarize our observations. The minority carrier concentration, the majority carrier concentration is equal to ionized impurity concentration plus electron hole pair concentration. The general formula for N type as well as P type semiconductors, right? What about minority carrier concentration? Under equilibrium, because recombination rate is equal to generation rate, please make note of this. Because recombination rate should be equal to generation rate, we obtain the formula minority carrier concentration into majority carrier concentration is equal to intrinsic concentration square. Let us write this down in symbols. So we are saying in N-type semiconductor, Nn0 into Pn0 is Ni square. In fact, in any semiconductor in general, N0 P0 will be equal to Ni square. Electron concentration into hole concentration will always be equal to Ni square in any semiconductor under equilibrium. I have already told you what is the meaning of equilibrium. Equilibrium means a silicon sample or a semiconductor sample to which no electric field is applied, no magnetic field is applied, no light is shining, it is completely isolated. Such a sample is said to be in equilibrium. So this is the formula. Now this comes from the fact that generation rate is equal to recombination rate. Okay. So this is summarized here in the form of equations. In N type, Nn0 is equal to Nd plus Pn0 approximately equal to Nd, and Pn0 minority carrier concentration of holes in N type semiconductor is Ni square by Nn0, that is approximately equal to Ni square by Nd, and similarly for P type semiconductor. Okay. So we will remember these two formulae which are very simple. Okay. That is, so N type semiconductor electron concentration is equal to donor concentration, and hole concentration is equal to Ni square by donor concentration. Now I leave it as an exercise to write a similar formula for P type. Okay, Pp0 is equal to what, and Np0 is equal to what. So you can write it yourself. We discussed about generation of electron hole pairs. Let's talk about how we discussed about creation of electrons and holes in semiconductor or mobile carriers. Let us talk about how once electrons and holes are created in semiconductor, they are transported. How do they move? We will talk about two methods of transport. One method is called drift. So when you apply a voltage to a semiconductor, a DC current, let us talk about DC voltage. To take a simple situation, you have a current I. So what is shown here is that the applied voltage creates an electric field E, which is given by minus gradient of psi, minus gradient of potential. Now as a result of this potential gradient, you have mobile carriers moving, electrons move from a negative terminal to positive terminal, because negative terminal is the source of electrons, and holes move from positive to negative terminal. So you have electrons and holes moving in opposite directions inside the semiconductor in response to electric field, but their currents add up. Okay, so this is drift mechanism. Another mechanism you have is diffusion. Supposing you shine light on a semiconductor and at one end electron hole pairs are created which are over and above the equilibrium value, because light creates additional electron hole pairs as compared to thermal energy. So now you will have hole and electron concentrations increasing at the surface as compared to inside bulk. In other words, you are setting up gradient of P and gradient of N. So gradient of P means hole concentration gradient, and gradient of N means electron concentration gradient. Electron and holes are more on the left hand face than on the right hand side. So they are diffusing. So electrons holes are moving in the direction of lower concentration. This process is called diffusion. It is somewhat like diffusion of gas molecules. Now as against drift, where electrons and holes move in opposite directions, in diffusion they move in the same direction as concentration gradient. As we will see, these carrier currents are consequences of directed carrier motion due to potential or concentration gradients superimposed over random thermal motion. So it is very important to understand the way we normally show current by straight arrows. This is only a part of the picture, okay. So let us look at the complete picture, how electrons and holes they move in a semiconductor. So we have said that this motion is to be regarded as superimposition of a directed motion over random motion. This is the key point. So let me distinguish it from motion of electron in vacuum, for example. So in vacuum, suppose I have an electron and I apply an electric field. So what will happen? The electron will move against the direction of electric field like this, right? So if I want to describe transport of electron in vacuum, it is against the direction of the electric field, it is in a single line, right? That is what it is. So there is only directed motion. So in vacuum, the transport of electrons is only directed motion. So whereas, look at the slide again, in semiconductors it is directed motion superimposed over random motion. This is a picture. So let us look at how electrons and holes move in equilibrium when no field is applied, no concentration gradient is applied, right? Isolated semiconductor. Like this. We just talked about how electrons and holes are created. Now what is their movement? Let us look at the movement aspect of this. So equilibrium picture, N-type semiconductor. You recall we had drawn a picture like this at the end of our discussion on how carriers are created. So at any instant of time, if you try to see the processes, they will look like this. At some points you have G, that is generation of electron hole pairs, and at equal number of places you have R, that is recombination of electron hole pairs. But in a large number of places you have I, that is ionization of the impurity. We are talking about an extrinsic semiconductor, okay. Now let us look at the motion aspect of the same picture. How these electrons and holes which are created, how are they moving? Now this is the picture of movement of electrons and holes which are created. Random thermal motion of electrons and holes. We are not showing G or R here, that is generation or recombination is not shown, which means we are assuming that the electron which is generated, it is remaining alive for all the time. Actually it will remain alive for some time and then it will recombine. So which means it will be generated, it will move about randomly, at some point it will recombine. So we are not showing the generation and recombination, that aspect, because the picture will become more complicated, right? What we are trying to see is between generation and recombination. Between generation and recombination, how will the electrons and holes move? So this is what is the motion. It is like dust particles in air. The red dot here is a hole and blue is electrons. So number of holes is less than number of electrons because it is a N-type semiconductor, right? We are talking about an N-type semiconductor. So electrons and holes move about like dust particles in air. This is the random motion, right? Now when you come up with an electric field or potential gradient or hole and electron concentration gradient, then a directed motion will be superimposed on this. How to visualize a directed motion superimposed over random motion? Let us look at that, because that is the picture in a semiconductor. Picture in vacuum is very clear, right? Look at the board. If you have an electric field, an electron will move in straight line like this, okay, it's very simple, only directed motion. But here Even when you don't apply, now in vacuum if you don't apply an electric field, what will happen to the electron? It will not move at all. There is no motion. In the absence of electric field in vacuum, no motion. But in the semiconductor, look at the slide. In the absence of electric field, electrons and holes are moving randomly, and they are moving randomly with a very high energy. Okay. Now what is the velocity of the electrons in random motion at room temperature? Can anybody tell me what is the value? This is called thermal velocity. Semiconductor in equilibrium at 300 K. So electrons and holes are moving like this randomly. What is the thermal velocity between any two collisions? At 300 K. Anyone can answer? That will give you an idea of how fast is this motion. Any college can put down the number and tell me what is it. Is there a response? Some of you have asked some other question that I am going to answer right later. First I want to know whether you have the answer to the question, what is the thermal velocity or speed of electrons at room temperature which are undergoing random motion. Okay, meanwhile I see a question here. Sir, can we say that if generation and recombination time is more than the electrons and holes will move of that much time? Okay, before I go to the question, a college from Pune, College of Engineering Pune has given an answer. The answer is 2.3 into 10 power 5 meters per second. They are saying 2.3 into 10 power 5 meters per second. They are very close. In silicon, this value is about 1 into 10 power 5 meters per second. So thank you College of Engineering Pune for that response. Okay. Meanwhile, let me go back to the question that I was trying to answer. Can we say that if generation and recombination time is more, then the electrons and holes will move for that much time? Now please understand, I think what you mean is if the time difference between the instant at which generation occurs and the instant at which recombination occurs, if it is more, then for the entire, that is called the lifetime, right? So if the lifetime is more, will the electrons and holes move? Yes. So they will keep moving around randomly between the generation and recombination, right? That is what will happen. So if I trace a path of an electron, it would be like this. Let us say at this point generation has happened. That means an electron has been created and a hole has been created. Okay, that is what has happened at this point. Now this fellow will move randomly and it will recombine somewhere here with another hole which has come from some other place, which was moving randomly. It came here, there is a recombination, here there is a generation. This hole is again moving randomly and it will meet some electron which may be moving like this. So here again you have recombination. So you can see between generation and recombination the carriers are moving randomly. Now why do they move randomly? It is because in the solid there are other electrons and holes. So no electron can move in one direction freely. It will come and collide with some other electron and hole and it will change the direction. And you not only have electrons and holes, you also have silicon atoms there vibrating, right? So there will be collisions, a large number of collisions. In vacuum, in the electron encounters no collision because there is nothing else in vacuum, right? But in a semiconductor you have other electrons and holes and silicon atoms. So because of that there are a large number of collisions and you get this random motion. Let us go back to the slide. Okay, so let us start with this random motion. Now superimpose a directed motion. How do you get? So here is an analogy which tells you how electrons and holes move when you apply an electric field. When you apply an electric field. So the actual movement of the electron or hole is as shown in the slide. Now what is being shown here is the movement of a hole. You can see that the carrier is moving from the positive terminal to the negative, so it has to be a hole, because you know that electron will move from negative to positive. So this is a hole. So it is not correct to show the movement of the hole as a straight line. That is not a correct picture. So normally the way we show is not the completely correct picture. So this is I, V, and we say inside the carriers are moving like this from, so hole is moving from the positive contact to the negative contact, like that in a straight line. That is not the way a carrier moves in a semiconductor. Then why do we show it like this? In your 12th standard, this is the way you have been exposed to, right? Because people don't want to present you a complicated picture when you are young. They want to show you a simple picture. But always remember, the simple picture has to be improved as you grow up. Because unless you make the picture more sophisticated, you cannot explain very many things. So instead of showing it like this, actual picture is random movement and directed movement. So a hole is moving from here to here, but in between it is moving randomly also. Okay, that is what is shown here on the slide. Now, so you can visualize this motion as follows. Imagine a box of sweets in open air. You must have seen like this in many shops. Okay, and imagine a dirty shop, a dirty place where you have lot of insects on the sweet box hovering around. Okay, lot of flies, let us say. So the way the flies move about over the box of sweets, it is like electrons and holes moving about in a semiconductor under equilibrium. Okay, so this is random motion. Now how can I get directed motion? Suppose I move the box of sweets to the right. Imagine you are holding the box of sweets and then slowly moving it to the right. Now what you will find is all the insects which are hovering around over the box will also slowly move to the right, because they always want to remain over the sweets. But even as they move to the right, they will always be flying around, hovering around randomly. So here is an example of a directed motion superimposed over random motion. When you move the box of sweets, the movement of flies is random motion plus a directed motion. That is exactly the way electrons and holes will move when you apply an electric field. Okay. So in this analogy, the carrier motion is like insect motion, and the force on carriers due to electric field is like longing of insects for the sweets. So insects are feeling a longing for the sweet, that is why they are moving along with the sweet box. Similarly, when you apply an electric field, the carriers which are charged, they have a longing for the electric field, so they move. So that is the way. So this is a picture you must hold in your mind of motion of electrons and holes in semiconductor. So now I have shown this picture, path of an electron and a hole. In this case, the red lines show the path of an electron. So you can see here that point G is generation. At this point, an electron hole pair has been generated. Electron is moving to the left and something like this. The hole is moving like this, the black. The hole is moving along the track which is in black color, and somewhere here it is meeting with some other electron which was moving around, and therefore recombination happened, right? So between generation and recombination, the time of the carrier is said to be the lifetime. Okay. Now let us define some quantities associated with this motion. So first important quantity is the root mean square velocity or thermal velocity. So this is called root mean square velocity because it is an average of the velocity for many carriers. You are now dealing with a large number of carriers, so you talk in statistical terms. You cannot talk about every individual carrier, right? So average. Now if you average the velocity of all carriers in equilibrium, you will get 0 because different carriers are moving randomly in different directions. So if I were to take any instant, if I were to take a snapshot, some instant t, I am looking at a semiconductor. Now I will find at that instant t, at any t, so one electron is moving like this, another one is moving like this, another one like this, another one like this, and so on. If I add up all these velocities, I will get 0. So I cannot take a simple average. I cannot take the average like V1 plus V2, suppose this is 1, this is 2, this is 3, this is 4, plus V3 plus V4, because velocity is a vector. So you have not only direction but also not only magnitude but also direction. So if I were to take average like this, which is arithmetic average for n carriers, then this average will be 0. So I cannot take this average. Then how do I capture the fact that there is motion? I know that there is a lot of motion, though it is random. So what do? I take root mean square, RMS average, root mean square average. That means I square, instead of V1, I take square of V1, V2 and so on. You know what is meaning of squaring a vector? It is a dot product. So V1 dot V1, okay, then the direction goes off. So root mean square average is calculated by taking square, then taking mean. I am taking mean because I am taking n particles, divide by n and root this. So this is V thermal. This is the root mean square velocity. That is 10 power 7 centimeters per second, or as someone from College of Engineering Pune said, it is 10 power 5 meters per second. In 10 power 5 meters per second, 10 power 7 centimeters per second. Please imagine what is this velocity, how much it is, right? Please to get a feel of how much this velocity is, you see, if I want to travel from Chennai to Bombay by air, if I want to travel from Chennai to Bombay air, how long does it take? How long does it take? Right? Let us say it takes about, say, 1.5 hours, and let's say the distance is about, roughly, let's put the distance as about 1500 kilometers. So aeroplane is flying at the rate of 1500 kilometers by 1.5 hours. I am taking a rough value. So 1500 by 1.5. How much is it? It is 1000 kilometers per hour. 1000 kilometers per hour aeroplane. Now please do this assignment. Compare this. This is per second you are talking about. So 10 power 5 meters per second is 100 kilometers per second. 100 kilometers per second. Right? So 100 kilometers per second. So per minute you multiply by 60. 100 into 60, 6000 kilometers per minute. That is really, now your aircraft is flying at the rate of 1000 kilometers per hour, and this electron at room temperature is moving at 6000 kilometers per minute. You can imagine how fast is electron moving at room temperature, right? Is really very high. That is thermal velocity, thermal speed. Mean free path between collisions, that is the second attribute of this random motion. What is mean free path? It is the length AB. So distance between any two collisions. So you can see here AB, this distance or that distance. Because picture is random, between different pairs of collisions you will have different paths. Now you take the average of all these, then you get mean free path. The word mean means average. So free path will be different for different collisions, different pairs of collisions. You take average of many, you take mean free path. Mean free time. Similarly, time between two collisions is called mean free time. So tau c is equal to mean free path LC by thermal speed, V thermal. And finally, you have what is called minority carrier lifetime. That is the time between generation and recombination of a minority carrier. Now please look at this. That minority carrier lifetime, tau minority, is greater than tau c, mean free time between collisions, but much less than majority carrier lifetime. Let us see why. You can see that from this picture that before recombination, after generation, it is undergoing many collisions. Between generation and recombination, a carrier is undergoing many collisions. This evidently means the lifetime of the carrier is much more than mean time between collisions, because otherwise there would not be so many collisions. Okay. Now, why is majority carrier lifetime more? In other words, majority carrier stays much longer than minority carrier, okay, after generation. Why? The reason is very simple. Minority carriers are very small in number. Suppose at any instant an electron hole pair is created in an n-type semiconductor. Now the hole will find itself in the midst of so many electrons, and therefore it can recombine with any of the electrons. It need not recombine with the same electron with which it was generated, okay, because so many other electrons are there, electrons are in majority. In other words, the hole is likely to recombine with an electron which was created much earlier than its birth, which means that therefore the electron lifetime is more than hole lifetime in n-type semiconductor, right. So the reason is majority carriers are too many in number as compared to minority carriers. Therefore a minority carrier after generation most likely meets with a majority carrier which is very different from that majority carrier which was created along with it, and therefore lifetime of a minority carrier is much less than lifetime of a majority carrier, okay. So normally in semiconductors when we use the term lifetime, it is always minority carrier lifetime. It so happens that majority carrier lifetime does not play a role in deciding characteristics of semiconductors, okay. Now let us come to the drift current and explain in terms of the picture of this random thermal motion. An electron subjected to an electric field achieves a constant acceleration A equal to minus QE by m naught in vacuum. However, if it is in a semiconductor, the electron if subjected to an electric field, it achieves a constant average velocity which is given by Vd equal to minus mu n E, okay, because it has to move through other electrons and holes in random motion which act like a viscous medium. This is the difference between motion in vacuum, that is this, and motion in semiconductor, okay. In semiconductor you have directed motion superimposed over random motion. So here again you can explain this with an analogy, right. Suppose I have a ball falling because of gravity, let us say in vacuum, then what will happen? This ball will accelerate with time, right, because of gravity. What is the acceleration? G. On the other hand, if the same steel ball is moving in a liquid, a viscous medium, in a tube, let us say, it is dropped, both are dropped at the same height, h. But if it is moving in a liquid medium, you will find that after dropping for some amount it will reach a constant velocity, whereas this is still accelerating with g. But this ball, this is let us say a viscous medium, oil for example. You might have done this experiment in physics. If you drop the ball in a viscous medium like oil, after traveling some distance it will reach a constant velocity, it will not accelerate like this. This is called terminal velocity. The word used to describe the velocity of the steel ball in a viscous medium is terminal velocity, okay. Why? Because there are two forces acting on this ball, one is gravity mg, and the opposite force because of viscous medium, friction from oil molecules, okay. So the frictional force becomes equal to the force due to gravity, and once the two forces are equal there is no net force on the ball and therefore it moves with a constant velocity. Now why does it travel to some distance before reaching a constant velocity? So it is accelerating in this region but finally it has reached a constant velocity. Why? Because the friction or viscous force is proportional to the velocity. If the velocity is more, frictional force is also more. So in the beginning its velocity is almost nothing because you have just dropped it, so frictional force is very small. As the velocity builds up, frictional force also builds up, ultimately two become equal, and then thereafter the ball moves with constant velocity. Same thing happens for electron in a crystal or in a solid, because it is moving through other electrons and holes which act like a viscous medium, which act like friction, therefore the electron achieves a constant velocity. So when you show a picture like this in which random motion is not shown even though it is there, you are trying to show that constant velocity that is achieved by the electron, directed velocity. So you are trying to show only the directed part of the picture. But after this class, you must always remember that the complete picture is a random motion and directed motion superimposed over it. We are only showing the directed motion here when we show a straight arrow like this. Now you can write the expression for a drift current density. It is Jn equal to minus Qn Vd, which is Qn into mu n into E, because drift velocity is electric field into mobility, mu is mobility. It is nothing but proportionality constant. So here we are saying that in semiconductor the velocity is proportional to the force, electric field, and therefore we are putting a constant, and that constant we are calling as mobility. For electron we put a negative sign because the electron moves, so Vdn, electron moves in the opposite direction to the electric field, that is why negative sign. If you write for holes, it will be Vdp equal to mu p into E, no negative sign here, right? Now the current is the charge into the concentration of the charges into the velocity. So charge is negative for electrons n, therefore minus q. Now substituting for Vd as mu n times E, you get Qn mu n E, and similarly for electrons, right? Jp is Qp Vd equal to Qp mu p into E. This is the formula for current, drift current. Now diffusion current. Electrons and holes in random thermal motion diffuse from regions of higher concentration to lower concentration, much like gas molecules. This diffusion can be understood as follows. Suppose I have a concentration gradient, right? Suppose I have, let me partition this semiconductor into different parts like this. Okay, let us say I have 16 electrons here, I have 12 electrons here, I have 8 electrons here, and I have 4 electrons here in this part. Okay. Now imagine they are in random motion, all these carriers. Let us take a one-dimensional situation. Now random motion means that out of these 16, 8 electrons will try to move to the right, whereas 8 will try to move to the left. So imagine it is a long semiconductor, right? And we are talking of some part. So this is 8 and this is also 8. Now similarly, out of this 12, 50%, that is 6 will try to move like this, and other 6 will try to move like this. Half, because they are in random motion. Random motion means a motion in any direction is equally likely. Out of this 8, 4 will try to move in this direction, and other 4 will try to move in that direction. Now out of this 4, 2 will try to move like this, and other 2 may try to move like this. Okay, let us concentrate on this part. Let us not bother what is happening here in this case and in these two regions, right? Let us concentrate here. Now what has happened is, because of this concentration gradient, that is the electron concentration is decreasing. Here it is more, less, 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 concentration gradient. If I try to see now across each of these planes, I will find that 8 electrons are moving from left to right, 6 from right to left, which means there is 1 electron net, 2 electrons net moving like this. Similarly here, 6 in this direction, 4 in this direction, net 2. Here similarly 2 in this direction. So you see that there is a net motion of 2 electrons in the rightward direction. If the concentration was the same throughout, if everything was 16, 16, 16, 16, 16, then this number 6 would have been 8, everywhere it would have been 8. So everywhere, if I take a plane, I will have 8 electrons crossing from left to right and 8 from right to left, if the concentration is same, 16 everywhere, right? So I will have no net motion, so this will be 0. If everything is 16, I will have everything 0. But because I have a gradient, you see I have 2 electrons moving to the right. Now if I increase the gradient, okay, or let us say I decrease the gradient. Instead of 16, 12, 8, 4, I have 16, 14, 12 and 10. Now what will happen is I have 8 moving like this, 14 means this becomes 7, 12 means this becomes 6 and 10 means this becomes 5. Now this 2 will change to 1, you can see that I have only one electron crossing from left to right. So I have decreased the concentration gradient. Earlier it was from 16 to 4, now it is only 16 to 10, right? So that is how you get diffusion, again because of random motion. Please note, if there are no random motion, there will be no diffusion current, okay. So diffusion is also superimposition of a directed motion or random motion. Now we can summarize our observation in the form of equation, and we can clearly see that if the gradient is more, then the current also is more. So we are writing the formula as shown here. The diffusion current density is proportional to the concentration gradient and can be written as, for electrons, Jn equal to charge into a coefficient like mobility, here you have diffusion coefficient into concentration gradient. So you are writing Jn is proportional to gradient of electrons, and remove the proportionality and put a constant here and put the charge to get the current, okay. So this is your formula. Evidently the unit of dn will be centimeter square per second. Why? Because Jn is current density, which is ampere per centimeter square, Q is coulomb, and gradient of n is dn by dx in one dimension. So dn by dx means per centimeter cube by dx centimeter. So gradient of n has this dimension. You can clearly see that if this is ampere per centimeter square, this is coulomb, and this is per centimeter cube per centimeter, then this is centimeter square per second. To do that dimensional analysis, so dn is equal to Jn by q grad n. Using this you can find out the dimensions, okay. You find out the dimensions of mobility in a similar way. Now for holes you see a negative sign here. For electrons there is no negative sign, but for holes there is. Why? This is because the direction of movement of the charge and current, the relative things. So if electrons are moving like this, so if you have n versus x like this, then dn by dx is less than 0 in this case. Now if electrons are more in concentration here than here, electron motion is like this, but current will be opposite to the direction of electrons. So current is in the negative x direction, this is positive x direction. So if the gradient is negative, current also is negative for electrons. Now if I change this to P, now what happens? The holes are moving in this direction, so the whole current is in this direction. So you can see that for holes the gradient is negative, but the current is positive in direction. Therefore in the formula you have a negative sign. That is what is shown here on the slide. Now let us explain the rectifying operation of a p-n junction based on whatever we have discussed, how carriers are created and how they move, right. So carriers are created by impurity ionization and thermal generation, and they move either by drift or by diffusion, okay. Based on this understanding, how do we explain the operation of various devices? Now let us begin with the rectifying operation of a p-n junction. This is the current voltage characteristics we want to explain. Forward direction high current, reverse direction very small current up to breakdown voltage. After breakdown again large current. So there are three regions: forward bias, reverse bias below breakdown, and breakdown. Let us look at these three regions. How do we explain? So we start with the simple situation, namely equilibrium, right. Even to explain drift and diffusion, You recall we took a semiconductor under equilibrium first, looked at how electrons and holes are moving in that, then we applied electric field or concentration gradient and saw how motion happens. We are going to use the same approach here. First start with equilibrium, no applied voltage, okay, that is this point. That is why this point is shown as a circle. So let me again show the flip back and show the slide. We are showing the equilibrium point. V is 0. How does a diode look like under this case? So here is the picture. Let us take a P plus N junction. Left hand side is heavily doped P type, right hand side is lightly doped N type. Now this is the junction here. You see we have a region that is called the space charge region near the junction. Let us explain why this space charge region forms. So when P region is brought into contact with N region, holes diffuse from P to N and electrons from N to P, setting up a positively charged region on the N side, that is here, and a negatively charged region on the P side, that is on this side, and therefore a built-in voltage. Okay, let us see how. So this is P plus. Now this is N. I am bringing N in contact with P. And I have joined it. Now just after I join, holes are more in number here than here. So there will be a tendency for holes to diffuse like this. Electrons are more here than here, more in N type than P type. So there will be a tendency for electrons to diffuse like this. So P region is losing holes, N region is losing electrons. Now we have already written what is the expression here for holes. The expression here is PP0 is equal to ND approximately. And what is the expression for electrons here? NN0 is equal to, PP0 is NA and NN0 is ND. So if the holes are lost from here, it will leave behind Na, ionized acceptors. That is what is happening. So on this side, when a hole moves away, it leaves behind an ionized acceptor, minus charge. Similarly, when the electron moves from N region to P region, it leaves behind a donor, and that can be shown like this. So that is why you have what is called a depletion region. Depletion region. The word depletion means removal. So because holes are, majority carriers are being removed from this side as well as from this side, you have a depletion of carriers. Now you might say, okay, holes are, this region is losing holes, but it is gaining electrons, is it not? So what is happening to these electrons? Yes, but these electrons are minority carriers in P region, their number is really very small. Okay, also there are large number of holes here, so electrons coming here can recombine, and therefore you are getting a region where you have ionized negative charge which cannot move, ionized impurities, Na minus, and here you have donors which are left behind by these electrons, Nd plus. Now you see the left hand side width, let us call it Xp for P region, and right hand side width, they are not equal. They are not equal. Why? Now you know that the charge on the right hand side should be equal to charge on the left hand side in magnitude. They are of opposite polarity. Why? Because every positive charge will need a negative charge to terminate. Now if the total charge here should be equal to the total charge here, but doping here is less as compared to doping here, and the charge is because of doping, as you can see. So if Nd is less than Na, unless I have more width Xn, I cannot get the charge here to be equal to charge here, right? So concentration of charge on the right hand side is less than concentration of charge on the left hand side, but total charge on the right hand side should be the same as total charge on the left hand side. Therefore, width here is more than width on the left hand side, right. So you can write it like this, supposing A is the area of this junction. So suppose the junction is like this, right. Now if I want to write the expression for charge in this region, this is xn. Let me show it clearly here. That this doesn't become complicated. Here, let me rub this off. So now the charge in this region xn is given by concentration of charge, that is charge per unit volume Nd plus into the volume of this region, which is the width, that is xn, and area, that is A, that is the volume, that is the total charge on this side, on the N side. I can similarly write the charge on the P side, Na minus into the width xp, that is this, into the area, that is volume. So this is the total charge. Na minus is the charge concentration, charge per unit volume. Na minus into xp into A, xp into A is the volume. So this total thing is now has no units, it is just number. Similarly this is number. Now if I cancel A, I get Na minus into xp is equal to Nd plus into xn. So since Na minus is more than Nd plus, this is, we are saying P plus, this is heavily doped compared to this. So Na minus is more than Nd plus. If I have this, if I want this equality, xp should be less than xn, right. That is what is shown here. In other words, now there is a field from positive to negative in this direction. This is referred to as the built-in field, and because of the field also, when I integrate the field over distance xp plus xn, I will get potential, because field into distance is potential. That is called built-in potential, normally represented as psi naught. So the simple picture you will find shown in books and so on is like this. So this is the built-in field, and psi naught is the built-in potential, right. That is the picture under equilibrium, V equal to 0. Equilibrium is reached when the field due to space charge sets up a drift tendency which exactly counterbalances the diffusion. Now we said that whenever P region is brought in contact with N region, electrons diffuse from N to P, holes from P to N. Question is, when will they stop diffusion? So they stop when this charge which is built up, which creates the field, it opposes the diffusion tendency exactly. So you can see that tendency for diffusion of holes is, so let me write here, diffusion, hole is in like this, and electron like this, because hole from P to N, electron from N to P, diffusion. Now drift is because of the field. So hole drift is like this, because positive to negative, and electron drift is like this, because it is in opposite to the direction of the electric field. So equilibrium is achieved when both these are equal and they cancel each other. Similarly both these are equal, okay. That is when this transfer will stop, and at the end of equilibrium you will have this xn and xp, where xp is greater than xn if Na is greater than Nd. This is Na and this is Nd, right. Now let us come to forward bias. Now V is greater than 0. Let me go back to the previous slide. So here there was no current, that is why on the IV map you are only showing this point under equilibrium, and there was certain depletion width here. Now moment I go to forward bias, you can see that the depletion region has become smaller, right. Concentrate on the depletion region here. I am flipping the slide. You can see that depletion width is reducing. Why? Because you can see the polarity of forward bias. P is positive, N is negative, this is external voltage. This is opposite to the direction of the built-in field. This is the built-in field. Let us put suffix 0 to show equilibrium situation. Now applied bias, this is positive, this is negative, forward bias, which means applied field is like this, or psi applied. So applied potential is opposite to built-in potential. Therefore, the net field in the space charge region is reducing, and that is why the width of the space charge region is also reducing. That is what is shown here. Now we want to explain how you get this current. So let us first write down what we have said just now. Applied voltage opposes the built-in voltage, reducing the field in the space charge region. Now this is the next thing that is happening, right? You can see that holes are being injected from P to N and electrons from N to P, and they are recombining. So that is what is shown by this arrow. So the positive contact is supplying holes which are getting injected into N region and recombining with electrons there, which are injected from the negative contact. This contact is also injecting electrons in the P region, which are recombining with holes here. So as written in the slide here, consequently drift reduces and diffusion dominates. Because of the applied electric field, drift reduces and diffusion dominates, causing injection of holes from P to N and electrons from N to P. You can see here under equilibrium we said for holes the diffusion tendency from left to right was exactly balanced by drift tendency from right to left. Now you applied an electric field from left to right. So this electric field will oppose the drift, because drift was right to left in equilibrium because of this. So drift is reduced, so diffusion is more. So diffusion is more means diffusion of holes is more, means holes will move from P to N when you apply a bias. Similarly, you can look at the electrons. Here also the drift will reduce, diffusion will increase, which means electrons will move from N to P. So you say electrons are injected from N to P, holes are injected from P to N. Now let us explain why you have generation here in this case. Now the sequence of statements is this: applied voltage aids the built-in voltage, increasing the field in the space charge region. Right? Applied voltage aids the built-in voltage, increasing the field in the space charge region. Reverse bias direction is, this is N is positive, P is negative. So reverse bias, N is positive, P is negative. Now this voltage is applied voltage, it is like this. So this is the applied field and applied potential, right? So this is in the same direction as this. Therefore the amount of field is increasing. Amount of field is increasing, therefore this region is expanding. Depletion region will now expand. Also the drift tendency in the space charge region will now increase as compared to diffusion. And you recall, if I take holes, the diffusion tendency is like this, but drift is like this, because drift is in direction of electric field, diffusion in direction of concentration gradient. Holes are more here than here, so diffusion tendency is like this. But in reverse bias what happens is electric field is being increased, it is sum of this field and that field, applied field, therefore this is more. So drift is more, diffusion is less, right? Therefore there is a tendency for holes to move from N to P. Holes are moving from N to P, okay, and electrons are similarly moving from P to N. You can argue similarly and show the electrons are moving from P to N. So drift tendency dominates over diffusion, causing extraction of holes from N to P and electrons from P to N. Now how can you get electrons from P to N? That is what is shown here. You see electron is blue, so electron is coming like this and going. Now electrons are minority carriers. Electrons are minority carriers in p region. How can you get minority electrons? They are very small in number. First of all, so you know that electron hole pairs are created by generation. Now for majority carriers you can have carriers because of thermal generation as well as impurity ionization, but for minority carriers it is only thermal generation. You have no other source. That is why what you are showing is a generation here. Electron and holes are generated. That's the only way they can be created in the p region, and that's the only way electrons can be created in the p region, and therefore these generated electrons are small in number, right? Similarly, generated holes here are also small in number, holes in n region. So electrons are minority carriers in p and holes are so in n, that is holes are minority carriers in n, leading to a small current for any applied voltage. So because your electrons have to move from p to n, but electrons are in very small number in p and holes are very small number in n. So now the current is going to be very small as compared to forward bias. So therefore that is why the current here is very small in the reverse direction as compared to current in forward bias. To give you an idea why the difference in current is so much, that is the current is in milliamperes range in forward bias but nanoamperes range in reverse bias, we can get a quick feel as follows. We realized that in forward bias holes are moving from p to n and holes are majority here. So you have a large source of holes. Let us see the relation between majority and minority carrier concentrations. So if I take, let us say p side Na equal to 10 power 18 or let us say 10 power 17 per centimeter cube. Now how many electrons will be here? So n p0 is Ni square by Na, this is Na, and for silicon Ni square at room temperature is 1.5 into 10 power 10 square by 10 power 17. So this is 10 power 20, so this will be 2.25 into 10 power 20 by 10 power 17, and this is equal to 2.25 into 10 power 3 per centimeter cube. So you see the electron concentration is only of the order of 10 power 3, whereas the whole concentration is of the order of 10 power 17 here. Therefore if the current is, because if this much of holes can give the current, then forward bias current will be 10 power 17, whereas this is 10 power 3. Reverse bias current is because of electrons from the p to n. So this number is very small. So that is why you can see that the current levels are very small in the reverse direction, nanoamperes, whereas here it is milliamperes. Milliamperes to nanoamperes, how much is the difference? 10 power 6. Milliampere is 10 power minus 3 amperes and nanoampere is 10 power minus 9 amperes. So 10 power minus 3 by 10 power minus 9 is 10 power 6 ratio. So you can see that it is somewhat like the ratio between the majority carrier concentration 10 power 17 and minority carrier concentration, right? Okay, we are talking about rectifying operation of a p-n junction. What happens if you are increasing your voltage beyond breakdown voltage? Then you are getting a very high current. Why? In the space charge region, electric field exceeds a critical value, E critical. In heavily doped junctions, space charge region is thin enough to allow a tunneling current of electrons across the space charge region from p to n. If you want to explain this, you cannot explain without considering quantum mechanics. So I will not try to explain it in this short session, right? I only want you to know this fact, that when the space charge region is thin, when the doping is heavy, then there will be a current as shown by this arrow here, extra current, that adds to already existing current, and this current increases rapidly with voltage. In moderately doped junctions, this I will explain a little bit more detail because it can be understood easily. Carriers drifting in the space charge region acquire high enough kinetic energy to break silicon-silicon bonds and generate electron hole pairs, which in turn generate more electron hole pairs, leading to an avalanche. So you see what is happening. There is extra generation in the space charge region shown by this. Why? Because consider a following situation. Suppose an electron is moving like this. Now, because the reverse bias is high, this width is high, electron can travel a long distance. It will gain a lot of energy while traveling. Electric field also is high. So the energy is so high that when it collides with the silicon atom will break, giving rise to electron hole pairs. So what is happening is like this. This is electron moving. At some point it is creating more electron hole pairs. The hole will move in this direction. Sorry, it should be the other way. Electron is moving from negative to positive. So electron moves like this. At some point there is a electron hole pair generation. The hole moves like this, electron moves like this. Now this hole while moving will generate another electron hole pair because the distance is large. So here suppose another electron hole pair is generated. So you get a hole and you get an electron that moves back. Now this electron can again generate an electron hole pair. So that is how what is happening is it is an avalanche. Okay, it's like a storm, positive feedback, right? One electron hole pair is generating large number of electron hole pairs, which in turn are generating more electron hole pairs. So this leads to an avalanche, and that is why you get a high current here and breakdown happens. Okay, let me pause at this point and ask, are there any questions? Can you show me some college from Andhra Pradesh? Aditya Institute of Technology. Oh, some question is there. Yeah, somebody is raising hand. Yes, please. What is the question?
Sir, temperature ఇవ్వడం వల్ల కరెంట్ ప్రొడ్యూస్ చేయొచ్చా సార్? సెమీకండక్టర్ లో గాని కండక్టర్ లో గాని
టెంపరేచర్ ఏంటి ఎక్కువ చేసిన తర్వాతనా?
టెంపరేచర్ ఎక్కువ చేయడం వల్ల సెమీకండక్టర్ లో గాని కండక్టర్ లో గాని ఎలక్ట్రిసిటీ ప్రొడ్యూస్ చేయొచ్చా సార్?
ఎలక్ట్రిసిటీ ప్రొడ్యూస్ చేయవచ్చా అది అడుగుతున్నావా? సరే, okay, let me translate this in English, whatever he has said in Telugu. What he is asking is, with the help of temperature, by raising temperature or supplying heat, can we generate current in semiconductors or metals? Please tell me, am I correct? Is this your question? Yes, is it your, did I frame your question correctly?
Yes, sir.
Yes, you can produce. So this is slightly away from what we are discussing, but let me answer the question. It is an interesting question. We said that we can apply a voltage and then get current I in a semiconductor. This semiconductor, you can get current even by diffusion. We have said that in PN junction we have explained how. So this is PN junction. When you apply a forward bias, you are getting I, V. Why? Because holes are diffusing to N and electrons are diffusing to P. Now, can you get current by applying temperature gradient? So you can see that yes, you can get current by applying temperature gradient. So suppose I have temperature T1 and T2. I am talking about semiconductor first. This temperature is T1 at this end and this is T2, right? How can I do that in practice? I can do it as follows. Supposing I have a silicon piece, I put a contact of metal on one side, one point. Another point, I put a soldering iron. This is soldering iron. So now this point will be hot and this point is cold, right? So temperature here is more than temperature here. You can actually get a current between these two. If I connect a galvanometer between these two, I will find a current, and the direction of this current will depend on whether this semiconductor is N or P. If the semiconductor is N, I will get particular direction. If the semiconductor is P, I will get the opposite direction of current. Now why is it happening? It is because the carriers are in random thermal motion, we have said, and the random motion is more at higher temperature. So wherever the temperature is more, so let us say temperature is more here in this case, this is hot, this is cold. So T2, greater than T1. Then random motion here is more, and random motion here is the velocity is less. Therefore, there is a tendency for carriers to move from here to here because velocity is more here and less here. So they will tend to move. Net effect is to movement from here to here. Now, if it is N-type semiconductor, electrons are moving from this end to this end. If it is a P-type semiconductor, holes are moving from this end to this end. Therefore, the current in the two situations is opposite to each other. And how will you get the current? If you close the circuit, then you will get the current through the wire. I will leave it to you as an assignment to find out whether the current is from hot to cold if it is N-type semiconductor, right? So outside the current is it from hot to cold? This is assignment given to you. Yeah, just do it. It is opposite if it is P-type. Does that answer your question? Please tell me. Adi question evaru adigaru varu cheppale. Answer ainda మీ question answer ainda లేదా?
సార్ అర్థం కాలేదు సార్ ఎక్స్ప్లెనేషన్ నాకు.
Oh, explanation అర్థం కాలేదా? What he is saying is he has not understood the explanation. Okay, have you understood the setup? Setup, I will explain again, but have you understood the setup?
సార్ అర్థమైంది సార్.
So okay, explanation, let me explain again. This is a semiconductor. Suppose it is P-type. Now it is the equilibrium, which means temperature is uniform. What will be the picture? Lot of holes are there. For any hole if I see, it will be moving randomly like this. It will have a thermal velocity, VTH. At this end also the hole is having the same thermal velocity, VTH. Supposing I now apply a temperature gradient. I say T2 is more than T1. Right? T2 is more than T1. Now this thermal velocity 2, because now thermal velocity will be more, whereas this thermal velocity is less. So VTH2 is more than VTH1 because T2 is more than T1. This velocity is more, this velocity is less. In other words, if I take a plane like this, right half of the plane will have more thermal velocity than left half of the plane. Now because carriers are moving randomly, a hole which is moving like this from left to right will have a thermal velocity VTH1. A hole which is moving from right to left will have a thermal velocity VTH2. Concentration is same here and here, but this velocity is less compared to this velocity, right? This is VTH2. So if this velocity is more than this velocity, evidently across this plane there is a net movement from right to left because the velocity is more. If it is equilibrium, T2 and T1 are same, this velocity is same as this velocity. Then there is no net movement across the plane. But now when T2 is different from T1, there is a net movement because VTH2 is more than VTH1. Now is it clear why there is a current?
క్లియర్ సార్.
Okay, thank you, now it is clear. So, but you must do the assignment. Please tell me, when I join and I put a galvanometer here, what will be the direction of current outside? Is it from hot to cold or is it cold to hot? If it is P-type, you can do the same thing for N-type. Okay. Okay, now let others do it. Let others do it and see. In fact, this approach can be used to determine the polarity of the semiconductor. Right. Any other questions? Let us see. Okay, sir, can you explain why majority carrier lifetime is more than minority carrier lifetime? That is one question. Next question is, what is the noise associated with the motion collision of electrons? Okay. Next question is, sir, can you explain once more how majority carrier lifetime is more? Okay, that I will. Sir, we are from Sri Vidyaniketan College of Engineering, Tirupati. My question is, why the mobility of electrons is greater than hole mobility? Okay, good. Let me explain one by one. Why majority carrier lifetime is more than minority carrier lifetime? Let's take that question. Yes, look at this picture. Okay, now this is an N-type semiconductor. You can see here that an electron hole pair is generated at this point. Okay, so this is the electron which is generated along with the hole. right? Let me draw this picture. Suppose at this point an electron and hole is created. So this electron, and let me use a different color for hole. This is hole. Now this is moving randomly. The electron is moving randomly and hole also is moving. Now suppose this electron again meets this hole somewhere here after some time and they recombine. So here there is generation and here it is recombination. Now what will you say? You will say the lifetime of this electron and this hole is the same because they were born together and they are dying together, right? Now this will be the picture in a pure semiconductor, intrinsic semiconductor. Suppose it is extrinsic, suppose it is N type. Now what will happen? So N type semiconductor, this is electron and this side is hole. Now N type semiconductor, there is large number of electrons. So after the hole has been created, right, even before it meets this electron here which was born along with it, it will meet some other electron, right? So it will not remain this long. What will happen is it is moving like this, somewhere here itself it will meet with an electron which was created some earlier time and it is moving randomly. Suddenly it came here, it met. So there is a recombination here. So now you can see that as compared to pure semiconductor, in N-type semiconductor, the hole, this is hole is meeting with an electron much earlier. Some other electron it is meeting because so many electrons are there. It doesn't have, it is not remaining long enough to meet this electron which was created here at this point, at this instant. Before that itself it is meeting some other electron and it is dying away. So this is what will happen. Minority carrier therefore will not remain very long as compared to that, as compared to majority carrier. This electron however can die only if it meets with a hole, but unfortunately holes are in very small number. So it will go on like this until it meets with a hole somewhere. So it will remain much longer. I hope it is clear. Now why minority carrier lifetime is less than majority carrier lifetime? Let us see the next question. If it is not clear, in the next class I will ask you in the beginning and then you can tell me at that point. Next question is why mobility of electrons is greater than hole mobility? You see, holes are moving because bonded electrons are moving. What is the difference between movement of electrons and movement of holes? So let me take this bond model. So there is a vacancy here, suppose, because electron hole pair has been created. Let us take pure silicon for simplicity. Now this electron is free to move, it will move something like this. Now what about movement of this vacancy? This is hole, how can it move? It can only move if another bonded electron gets into this place. So suppose this electron gets in here, then this will be established, so vacancy has moved here. Then if this electron gets in here, then it has moved here. Then if that electron gets in here, it has moved here. So the vacancy is moving via bonded electrons. Please remember this, the vacancy is moving via bonded electrons, whereas the free electron is free to move everywhere. Vacancy can only move via bonded electrons. Since vacancy is moving via bonded electrons, its mobility is less as compared to mobility of free electrons. Now there was just one more question. What is the noise associated with motion collision of electrons? What is the noise associated with motion collision of electrons? It is like this. Now because electrons and holes are in random motion like this, if I try to see at any plane, okay, sometimes I will detect the presence of an electron, sometimes I will not detect it because electrons are in motion. Let us say I take this contact. So sometime an electron is coming and striking it, and again it is moving. Similarly, hole is striking. So if I were to stand here at this end and watch at any temperature greater than 0 K, sometimes there will be occasions when I will detect an electron here, okay. In other words, a moving electron is nothing but a current. So I am likely to detect currents at different points of time because of the random movement at this contact. And now the current can be both ways, it is rightward as well as leftward. So if no applied voltage is there, net current across any plane is 0, but I may detect some current from left to right at some instant, and some other instant I may detect current from right to left because of the movement of electrons, random movement. If temperature is 0, then there is no movement of electrons, then everything is calm, I don't feel anything like this. But if temperature is greater than 0, there is a random movement, because of it at any point I will detect currents at different instants of time. Sometime the current will be in one direction, sometime it is in the other direction. So this is what is the source of what is called noise, because this current is not in any one direction, it is random at different points of time. So you can say this is a simple explanation of why there is noise. Okay, next another question is, why there is no concept of holes in conductors, right? Why there is no concept of holes in conductors? Now that I mean you mean metals, okay. So the mechanism of generation of carriers in metals, you have to look at that. So if you take a metal, how do you get electrons? Supposing you take aluminum. So what is happening is, there is a positively charged aluminum atom, a nucleus, and it has electron. So each atom is providing one electron. Each aluminum atom is providing one electron, okay. So in metal the picture is electrons and ionized nuclei, ionized atoms. Now the ionized atom does not move, right? Positively charged atom does not move. The bonding in aluminum is different from bonding in silicon. In silicon you have covalent bonds, which when the bond breaks you have a vacancy, lack of an electron, and via this vacancy other bonded electrons can move. The bonding in aluminum is not covalent, it is ionic, okay. Therefore when an aluminum atom gives away an electron and the electron is free to move, there is no vacancy like thing as you have in silicon, in aluminum, via which electrons from other aluminum atoms can move, right. So you can see in aluminum what is happening at 300 K, let us say every aluminum atom is giving an, now in fact in metal even at T equal to 0 K, every aluminum atom will give an electron, okay. Whereas in silicon at T equal to 0 K no electrons are available and no holes also, because all of them are participating in bonding, covalent bonding. Even at T equal to 300 K, all silicon atoms cannot break because the bond strength is very high, 1.1 electron volt, right. So the covalent bond is a strong bond, so not all bonds can break. So we have seen that only a very small fraction of silicon atoms are ionized, that is number of atoms is 5 into 10 power 22 per centimeter cube, whereas number of broken bonds is 1.5 to 10 power 10 per centimeter cube at temperature T equal to 300K. Whereas in the case of aluminum, all aluminum atoms are ionized. Even at T equal to 0K, they can give electrons. Their electrons are available, free. Okay, so there is no question of creation of electron hole pairs here. Suppose all silicon atom bonds break, you would not have any holes here, right? In fact, the silicon will melt, right, if all bonds were broken. So the bonding in silicon in semiconductor is different from bonding in metal. Okay, so if you want to explain in terms of energy band diagram, one can give a simpler explanation, but then you have to first understand what is the energy band diagram of semiconductor and metal. So once you understand the complex idea of energy band diagram, explanation becomes simple. So in terms of a simple explanation for in terms of the bond model, this is what you can say, right? Whatever I have said just now, why there are no holes in metal. P-type silicon sample, high conductivity compared to N-type sample having same dopant concentration. Why? P-type silicon sample, no, it is the other way around. If the doping is same, P-type silicon sample has lower conductivity compared to N-type sample because mobility of holes is less than mobility of electrons. Okay, so we have answered why there is no concept of holes in conductors, right? You have only electrons. Absolute zero temperature, what is the picture of atom? Do the electrons still rotating around the nucleus? Picture of atom. Okay, now please understand the concept of temperature is valid only for a collection of atoms. You don't have anything like temperature for an isolated atom, right? Please understand this. So only when you put atoms together as in a solid and you have a large number of atoms, right, only then the concept of temperature arises. And what is temperature? It is the degree of random energy present in the crystal at any temperature, because at any temperature when you form a solid, this solid at any temperature, all atoms will vibrate about their positions, right? Because what is temperature? Temperature is heating. It is the heat energy. It is the index of heat energy. So how do you raise the temperature of a sample? Let us say this is a sample solid. Now how do you raise its temperature? You bring another solid which is at a higher temperature and bring it in contact with this. Then that solid will transfer its heat energy to this solid. Now what do you mean by saying the other solid? Let us say I am bringing this solid in contact with this. What do you mean by saying this temperature is higher than this temperature? The random energy associated with the random vibration of atoms here is more. So when you are touching this body to this body, these randomly vibrating atoms will transfer their movement to this atoms of this solid, right? And that is why these are also now started vibrating. That is how temperature of this has increased. So first point is, you are asking about the picture of atom at 0 Kelvin. You should be sure whether you are talking about an atom in a solid or an isolated atom. If it is an isolated atom, there is no concept of temperature because there is no random energy, right? This happens only when atoms are brought together and they are bonding to each other and then so on in a solid. So isolated atom, no concept of temperature, right? If you are talking of an atom in a solid at T equal to 0, what is the picture of atom? Well, yes, as you have said, there is a nucleus and there are electrons revolving around it, but you must always also know that there is bonding, because temperature concept is applicable only in solid. In a solid, one atom will be bonded to another atom by various means. You know, there are various bonds, covalent bond, ionic bond and so on. So there will be bonding. So surely electrons will be revolving around nucleus, but they will also be participating in bonding with neighboring nuclei. So it is, the picture is little bit more complicated than an isolated atom. So I would say the picture of an atom which is isolated is much simpler than the picture of an atom in a solid at T equal to 0 K, because the electrons which are surrounding the nucleus of an atom are also being influenced by other atoms and they are participating in bonding. There have any mobility of electrons and holes for intrinsic semiconductors? Yes, electrons and holes have mobilities, right? Even in intrinsic semiconductor, in fact, the mobility of electrons and holes in intrinsic semiconductor is higher than mobility of electrons and holes in extrinsic, because evidently in extrinsic semiconductor you have impurities, right, with which the electrons will collide and their mobility will decrease. In a pure semiconductor, no impurities, so number of collisions is less, so mobility is higher. What are special advantages of carbon as semiconductor material? So nowadays people are exploring carbon in the form of diamond, for example, right? So it has to do with the energy gap. Energy gap of carbon is, energy gap of diamond is very high as compared to energy gap of silicon. Therefore it can be used at higher temperatures. Also it will not, it is not so easy to generate electron hole pairs by electromagnetic field and so on. So it will be radiation, it will be radiation hardened material, that is radiation cannot, if you make devices in diamond then radiation cannot affect the operation of the device, right, because it will not disturb the device because band gap is more. So high temperature operation, then protection against radiation, these are some of the advantages. Once more for the final session tomorrow. Thank you.